Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will be talking about the different aspects of dipole in an electric field. For example, the torque acting on a dipole in an electric field, the work done in deflecting a dipole in an electric field, and the potential energy of a dipole in an electric field. This topic is meant for class 12 students of CBSE, ISC and different state boards. This will also be found useful for students appearing at different competitive exams like NEET and JEE Mains. The complete note of the topic is given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. We will first find out the torque on a dipole placed in a uniform electric field. So consider a dipole AB with a charge plus Q at the end A and charge minus Q at the end B. The dipole axis makes an angle theta with the direction of the electric field. The length of dipole is 2L. Since electric field is defined as the force acting on a unit positive charge, the force acting on the end A where we have a charge plus Q is QE in the direction of the electric field. And the force acting on the end B where we have a charge minus Q is also equal to QE, but it is in the opposite direction, in a direction opposite to the direction of electric field. These two forces at A and B ends are equal in magnitude but are anti-parallel to each other. The perpendicular distance between these two forces is AP, and from this triangle ABP it is easy to see that AP is equal to 2L sin theta. So these two forces form a couple which has a tendency to align the dipole in the direction of the electric field. The moment of this couple is known as torque. So the torque acting on the dipole is tau is force into perpendicular distance between the forces. The either force is QE and the distance between them is AP. Distance means the perpendicular distance. So this is QE into 2L sin theta. So this is 2LQ into E sin theta. We can write it as this is equal to 2LQ into E sin theta. Now 2LQ is nothing but dipole moment P. So tau is equal to PE sin theta. Is dipole moment of the dipole. So as the torque, dipole moment and the electric field are all vector quantities, equation 1 can also be expressed as tau equal to P cross E. Okay, because A cross B is AB sin theta. So P cross E is PE sin theta. Obviously, the torque acting on the dipole is maximum when theta is 90, because sin 90 is 1. Remember, so the torque acting on the dipole is maximum when theta is 90 degrees. That is when the dipole axis is inclined to the electric field at right angles. The maximum value of torque acting on a dipole in electric field is tau maximum is PE. Clear? Next we come to work done in deflecting a dipole in an electric field. Just now we have seen that when an electric dipole is inclined to the direction of electric field at an angle theta, a torque acts on it, the magnitude of which is given by PE sin theta. Suppose the angle of deflection of the dipole from the electric field increased from angle theta to theta plus d theta, so that the angular displacement of the dipole is d theta. So the work done in this process, and that is given by dW is torque into angular displacement. Torque is tau angular displacement is theta, because we have increased the angle from theta to theta plus d theta. So put the value of tau here. So tau is p sine theta and this is d theta. And therefore, the total work done in deflecting the dipole from theta equal to 0 to theta equal to theta is then given by the integral of equation 4. So W is equal to integral of dW. This is integral of Pe sine theta. The limits vary from 0 to theta. So if you integrate it, this gives you W equal to Pe into 1 minus cos theta. So from equation 5, it follows that the maximum work is done in deflecting a dipole through an angle of 180 degree from the direction of electric field, and this maximum work done is W maximum is Pe into 1 minus cos 180 degree. Why this is so? Because you already know that cos theta is minus 1 when theta is 180 degree. So you can write here Pe cos 1 minus theta. So W is Pe into 1 minus cos 180 degree. So this is Pe into 1 minus 1. Okay. So this is simply 2Pe. Clear? So maximum work is done in deflecting the dipole through an angle of 180 degree in the electric field. So maximum work done is 2Pe. Okay. Next we come to the potential energy of a dipole in a uniform electric field. We have seen that work has to be done in deflecting a dipole in a uniform electric field. This work done is stored in the dipole as its potential energy. That is, W is the work done, is delta W means change in potential energy. So this is the difference of final potential energy minus initial potential energy. So delta U is equal to UF minus UI. UF is the potential energy when deflection from the electric field is theta 2, and UI is the initial potential energy when the deflection from the field is theta 1. So we have W is equal to integral of dW Pe sine theta d theta. The limits vary from theta 1 to theta 2. So this is Pe into integral of sine theta d theta, and the limits vary from theta 1 to theta 2, and this can be written as minus Pe cos theta 2 minus Pe cos theta 1. So if you compare equation 8 with equation 7, it is easy to see that minus Pe cos theta 2 is the final potential energy of the dipole in the electric field, and minus Pe cos theta 1 is the initial potential energy of the dipole in the electric field. Okay, so the potential energy when the dipole is inclined at an angle theta with the electric field is simply minus Pe cos theta, and this can be written as minus P dot E. Okay, it follows from equation 9 that the potential energy of an electric dipole is a function of angle of deflection theta from the direction of electric field. Different cases may arise. We may have different values of theta, but we will consider only 3 particular cases. First of them is when theta is 0 degree. When theta is 0, that is, when the dipole axis is parallel to the direction of electric field, then its potential energy is minus Pe. So U naught is minus Pe. When theta is pi by 2, that is when the dipole axis is perpendicular to the direction of electric field, then the potential energy is U pi by 2 is 0, because cos 90 is 0. And when theta is pi, that is when the dipole axis is anti-parallel to the direction of electric field, then the potential energy is U pi is equal to minus PE because cos 180 degrees is minus 1. Okay, so we have minus PE cos 180 degree. This is minus PE into minus 1. So this is plus PE. Okay, this is what we have written here. So you see that the potential energy of a dipole is minimum when its axis is parallel to the direction of electric field. And in this case, it is a state of stable equilibrium for the dipole. कोई भी सिस्टम उस समय स्टेबल इक्विलिब्रियम में है रहता है जब उसका पोटेंशियल एनर्जी मिनिमम हो. So system remains in stable equilibrium only when its potential energy is minimum. So when theta is 0 degree, that is when dipole axis is parallel to the direction of electric field, then the dipole's energy is minimum, or it has minimum value of potential energy. So in that case, the dipole remains in stable equilibrium. Similarly, when the potential energy of dipole is maximum, when its axis is anti-parallel to the direction of electric field. That is when theta is 180 degree. When theta is 180, then the potential energy is plus P. So this is the maximum value of energy. So this is a state of unstable equilibrium. So in this lecture, we have seen what is the torque acting on a dipole when it is placed in a uniform electric field. What is the work done in deflecting dipole in an electric field, and what is the potential energy of a dipole when it is placed in an electric field at an angle theta, where theta may have any value. I assume you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.